In this video, we will do another example about vector equations, and here we are asking the question, if possible, the given vector B054, express it as a linear combination of the vectors A1, A2, and A3. Okay, in class we said that linear combination of vectors is just a combination of the following type. Okay, so the question here is whether there are weights x1, x2, and x3 such that this equation is satisfied. So the question is x1, x2, and x3. How much are they, right? So as we said in class, right, you can express this, multiply x1, x2, and x3 by the vectors a1, a2, and a3, multiply the weights within the vectors, then add the vectors, and then you're gonna get a something very similar to system of linear equations. Or in order to speed up the process, because we know that we can observe system of linear equations also as vector equations, what do? We just jump into constructing this augmented matrix -2, 9, 6. As you can see, the vectors here are going to be columns of my matrix, -3, 2, and 1 for A2, and 1, 7, and 5 for A3 is equal to B0, 5, 4. And now you have to row reduce this matrix, so we can just this here is going to be our pivot position, and in order to get a pivot position there, we can just multiply the row 1 by -2, so -1/2 times row 1 is row 1, and we get 1, 3/2, -1/2, 0, 9, 2, 7, 5, and 6, 1, 5, 4. Now that I have obtained 1, I need to eliminate these two values. So that means first I'm gonna start eliminating this 9, so that's row 2. 9 minus 9 times 1 is 0, minus 9 times row 1 becomes row 2. So let's see, what do we get? 1, I'm not changing row 1, so 1, 3/2, -1/2, 0. 9 minus 9 is 0, okay? 2, so what do we have here? 2 minus 9 times 3/2 is equal to 4 minus 21/2, which is -17/2. And then 7 minus 9 times -1/2, that's 7 plus 9/2, which is 14 plus 9/2, and that's 23/2. And here I have 5 minus 0 is just 5. Okay, and here I'm also going to do something similar with row 3. So I want to eliminate 6, so 6 minus 6 times 1 is 0, so row 3, sorry, minus 6 times row 1 becomes my new row 3. 6 minus 6 is 0. 1 minus 6 times 3/2 is equal to 1 minus 9, that's -8. And then 5 minus 6 times -1/2 is equal to 5. 5 plus 3, and 5 plus 3 is 8. And then 4 minus 0 is 4. So I just want to make sure that I did this correctly. Let me just check this row right here. This row right here, so 2 minus 9 times 3 over 2. Bring it under common denominator, that's 4 minus 27, sorry, not 21. 9 times 3 is 27, 4 minus 27 is negative 23. So negative 23, okay? So what is going to be covered, because I got the leading one and obtained 0, we need that leading one, find the next leading one, cover the first row. What is going to be the pivot column? This is the pivot column, so this needs to become a leading one, so I'm going to multiply the second row by negative 2 over 23 to become row 2, and then I get 1, 3 over 2, negative 1 half 0, 0, 1, negative 1, and that's negative 10 over 23, right? Negative 10 over 23, and then I'm going to do, and here you can have, okay, 0, negative 8, 8, 4, although you can just simply multiply everything by 8, but doesn't matter. And finally, eliminate this term right here, so that's row 3 plus 8 times row 2 becomes new row 3. I'm eliminating, so this is the leading one, and now I'm eliminating the entry, need the leading one. 1, 3 over 2, negative 1 half, 0, 0, 1, negative 1, negative 10 over 3, and here I have negative 8 plus 8, 0, 8 minus 8, 0, and then here I get 4 minus 80 over 23, so that's how much, 92 minus 80 over 23, and that's equal to 12 over 23. And what do we have? I get that this system is inconsistent. Why? Because I have a leading one in the augmented column, right? Or I have a case where I have 0 plus 0 plus 0 is equal to 12 over 23. So this implies that the system is inconsistent. Or in other words, B cannot be expressed as a linear combination of the given vectors. Or the same sentence, the same idea, we can just say that B does not belong to the span of A1, A2, and A3. Okay? So these three statements are equivalent. What would this mean geometrically? So we have vectors that live in R3, right? These are three-dimensional vectors. And as I can see, this particular vector B cannot be obtained by any linear combination between A1, A2, and A3. Any linear combination. Okay? That means that all of the linear combinations between A1, A2, and A3, they don't fulfill the whole three-dimensional space, or mathematically said, they don't span 3D. They don't span the whole three-dimensional space. Why? Well, it's obvious. There are some vectors that simply cannot be expressed by a linear combination of these three vectors. Okay? So a very relevant question now would be, well then, what is the span of these three vectors? Okay, what do they span? What would be geometrical interpretation of the span of this? Or in other words, what would be the geometrical interpretation of all the linear combinations of these three vectors? Okay, another thing that we're going to that we mentioned is that the fact that these three vectors don't span the whole three-dimensional space, that means that their linear combination, their span is a plane. Okay, so that means that their span is a plane, and we will determine that by the next question. So it's the same thing, describe the span of these three vectors. Okay, so I give you the same vectors and I'm asking you, well, okay, what is the span then? We saw with the previous example that that's definitely not the three-dimensional space, right? So what their span looks like. So basically I'm asking you now the question, right? For any, what do we get if we any vector b, right? Let's call that any vector, I don't know, u, where u has the most general form a, b, c, right? I don't know how much are a, b, c. So I want to find the relation between these such that this system would be consistent, or spoken with the language of this particular section, such that this vector equation will be satisfied. Okay, for what u with entries a, b, c, okay, would satisfy this vector equation. Okay, or in other words, what vectors can come up from any linear combination of these three vectors. Okay, so there you go. Once you have set up the equation, basically you should know now what to do. You should create this matrix, the same that we did, -2, 9, 6, -3, 2, 1, 1, 7, 5. And now I put the most general vector, three-dimensional vector, that's a, b, c, right? I don't know what are these values. Basically, I want to know the relation between these values so that this vector equation will be satisfied. Because I have already reduced this matrix, I will follow the same elementary row operations as before, right? So first is -1/2 times R1 becomes R1, so I'm copying it from the previous problem, right? And then I'm gonna save some time because this coefficient matrix here, I'll just have to copy it from here, and I just have to check what's gonna happen at the end, right? So 1, 3/2, -1/2, 9, 2, 7, 6, 1, 5. And then this is just -a/2, b and c, right? -a/2. Now I have this row 2 -9 times row 1 becomes row 2, so row 1 stays the same, 1, 3/2, -1/2, -a/2. Row 2 -9 row 1 is, again, I'm not doing this calculation, I'm just copying this 0, -23/2, 23/2, and then I have row 2, which is b, -9a/2. So b minus 9, so that's plus 9a/2. And here we had row 3 -6 times row 1 gave us 0, negative 8, 8, right? And now C minus 6 times row 1. So C minus 6 times negative A over 2. This and this cancels, is 6 plus 3A. So C plus 3A. Okay. Now the next row operation was negative 22 over 23 R2. I get 1, 3 over 2, negative 1 half, negative A over 2, 0, 1, negative 1. So I get this times negative 2 over 23. So negative 2 over 23 times, if I bring this under common denominator, that's 2, 9A plus 2B. And then I copy this row here, 0, negative 8, 8, and 4. And finally, row 3 plus 8 times row 2 becomes row 3. So I don't have space here. So I get 1, 3 over 2, negative 1 half, negative A over 2, 0, 1, negative 1, and this negative. So these two can cancel. So it's negative 9A minus 2B over 23. And finally here I have 0, 0, 0. And this is 4 plus 8 times negative 9A minus 2B over 23. In order this system to be consistent, this entry here has to be what? This entry here has to be 0. And how did I get here? So here is, oh my god, sorry about that. So I copied it wrong. This is C plus 3A, C plus 3A, my bad, sorry. So instead of 4, it should be C plus 3A. Okay, so this entry here has to be 0 in order the system to be consistent. Okay. So let's see, what does that mean? We need C plus 3A plus negative 72A minus 16B over 23 to be equal to 0. Okay, so let's see further on. This means bring this under common denominator, 23C plus 69A minus 72A minus 16B is equal to 0 over 23. And now you can multiply both sides by 23. And you can get, how much is this? Negative 3A, right? Negative 3A minus 16B plus 23C is equal to 0. So in order this vector equation to have a solution, the relationship between these entries in the vector has to satisfy this equation. Okay? Or in other words, only the vectors whose entries satisfy this equation, okay, only vectors whose entries satisfy this equation can be expressed as the linear combination of these three vectors. But if I take A stands for X, B stands for Y, and C stands for Z, right? So if I multiply this by -1, you have 3x plus 16y minus 23z is equal to 0. What is this? Nothing else but an equation of a plane in R3, right? So in 3D, this is a plane, two-dimensional plane in 3D. That exactly, this particular plane is the span of these three vectors. Okay, so these three vectors, they lie in a plane, okay, and the linear combination of them produce this particular plane.